Okay, now that we've got some concentration units out of the way, we dive into the real meat of the atmospheric reactions at ground level. And the thing that I cannot stress enough is that hydroxyl radical, that OH species with an unpaired electron on oxygen, is the tropospheric sink. The vast majority of all of the oxidation reactions that occur in the troposphere revolve around this species. And so if we're talking about oxidation reactions, well, what species exactly are getting oxidized? Well, it's helpful to mention that there are both natural emissions and anthropomorphic emissions of a number of species that then undergo oxidation in the atmosphere. And under the natural emissions, there are a number of partially oxidized species. So refer back to the appendix video for a little bit more clarification on partially oxidized and fully oxidized or fully reduced species. But here, this is as an example, we've got carbon monoxide, we've got nitric oxide or sulfur dioxide as partially oxidized species. And then there's also a number of fully reduced species that are also emitted into the troposphere. And those include things like ammonia or hydrogen sulfide or methane. There's natural sources for all of those gases. But then in addition, what we spend a lot of time talking about are those anthropomorphic emissions, things that come from human activity. And a lot of it comes from burning things, fire processes, or particularly automobile traffic or transportation is where many of these emissions come from. And there's the emission of fully and partially reduced hydrocarbons. So things like formaldehyde, ethanol, carbon monoxide, many other hydrocarbons in various forms of oxidation. And then also nitric oxide and nitrogen dioxide are both common emissions, as well as sulfur-containing compounds like hydrogen sulfide and sulfur dioxide. And the really important thing to stress is that all of these partially oxidized species undergo oxidation in primarily the troposphere, and then are either removed or fully oxidized entirely up to, for example, CO2 would be the fully oxidized form of carbon there. But it's the OH radical, it's that hydroxyl radical that initiates the process of oxidation for nearly all of these. Even though it exists in extraordinarily low concentrations, the oxidation events don't begin with the reaction with diatomic oxygen because the activation energy barrier for that reaction is too high. But OH itself, the activation barrier for reaction with many of these is quite low, and it is the species that initiates these oxidation processes. Now, where does OH radical come from in the troposphere? Well, it actually comes from, at the very beginning, trace amounts of ozone that exist in the troposphere. And there's a number of sources of those. We'll get to that later. But remember that, that ozone can be broken down by UVB light to generate an excited O2 molecule and an excited oxygen atom. And so if there's some UVB light, which there is, and particularly if we've got ozone destruction occurring in the stratosphere, we're going to have more UVB light. But essentially, the key point here is that we get a trace amount of this that generates then a trace amount of that excited oxygen atom, shown here. And that excited oxygen atom reacts with water to form two hydroxyl radicals. And this reaction you might remember from the story last week. We'd done some enthalpy calculations to show that this reaction is unfavorable if the oxygen atom is not in its excited state, but it is favorable if the oxygen atom is in an excited state. Also, it's important to point out that the concentration of water is much higher in the troposphere than it is in the stratosphere. And so the likelihood of that excited state oxygen atom finding water molecules much higher in the troposphere than in the stratosphere. But this is where those hydroxyl radicals initially come from. And we can look at the concentrations. I mentioned they were very low. They're on the order in the troposphere of about 10.9 times 10 to the minus fifth molecules per cubic centimeter, or to put that in kind of a ppx scale, that's less than 1 part per trillion. That's about 0.0435 parts per trillion here in the troposphere. In the stratosphere, a hydroxyl radical also exists in the stratosphere. The concentration is a bit lower, and that may surprise you at first, since you'd probably expect there to be a much higher concentration of these excited state oxygen atoms due to more ozone being photolyzed and dissociated in the stratosphere. However, remember that the concentration of water molecules is extremely low in the stratosphere. And so as a net, we end up with a lower overall concentration of hydroxyl radical in the stratosphere, about 1.1 times 10 to the minus fifth molecules per cubic centimeter, or 0.00439 parts per trillion. Now, the average lifetime of that hydroxyl radical is about 1 second in the troposphere. It's a very reactive species, and as we'll see, it can react with a number of molecules, and so it's quickly consumed after it is formed, but as we'll see, it's eventually reformed. So what reactions can hydroxyl radical undergo? Well, there's a couple. If it bumps into a species that contains multiple bonds, so a double or triple bond, providing that that species is stable, then generally we will get addition of the radical to that bond. So you will essentially just add the OH onto that molecule, and you will break one of the multiple bonds. So if it's a double bond, you would probably go down to a single bond, or if it's a triple bond, you go down to a double bond. That's sort of illustrated here, where reaction of hydroxyl radical with carbon monoxide, you add to the carbon and end up breaking one of these triple bonds to leave you with a double bond. And now I have indicated with a little dot here that carbon in this resulting molecule has a radical on it. A radical is simply a term for an unpaired electron. And so carbon now has an unpaired electron. Its valence is not filled. It would only have 7 valence electrons around it. Additionally, we can have addition of the hydroxyl radical here to a carbon-carbon double bond to generate, it simply adds to one of the carbons, and then you end up with the radical, the free radical on the other carbon. And then we could also have it add to, say, sulfur dioxide, where normally the sulfur has 2 double bonds to the 2 oxygens, and you add and end up with an unpaired electron on sulfur in this case. Now, in addition to these addition reactions, we can also have abstraction. So if a species contains a hydrogen, but it doesn't have any double bonds, then most likely we are going to get H atom abstraction. So the OH radical will come and pull a hydrogen, and that hydrogen will take 1 electron from its bond, from that bond, and bring it with it. So what we see here, for example, if we react hydroxyl radical with ethane, the OH comes and simply plucks off a hydrogen atom with its electron going with it, and that leaves then an unpaired electron on the ethane, so now it's an ethyl radical, and we've formed water. We can also do this with NH bonds or SH bonds to pluck off those and leave you with nitrogen or sulfur-centered radicals and water. But we do not see this occur if you try to react hydroxyl radical with HF. This reaction does not occur. And given some of the conversation that we've had from class early this week, on Monday when we talked about bond strengths, you might be able to rationalize what is going on here, why we see this reaction being favorable for CH, NH, or SH bonds, but not for HF. And that comes from looking at the bond strengths. So the bond strengths of the new bonds that we form has to be greater than the sum of the bond strengths that we break in order for this reaction to be exothermic or favorable. So here, if I look at in this top reaction here, I'm breaking a CH bond, which is about 411 kilojoules per mole, but I'm forming an OH bond, so that's 459 kilojoules per mole. So in this reaction, the way that we draw our enthalpy is bonds broken minus bonds formed, and so 411 minus 459 is going to leave you with a negative number, and so this reaction will be exothermic. You can see a similar trend for the NH bond, so that's 386, so that's a weaker bond than the OH bond that we form. Same with the SH, that's a weaker bond than the OH bond that we form. But not the FH bond. The FH bond is a stronger bond, and thus it's not favorable to break that bond to form a weaker OH bond. And so that reaction is endothermic, actually quite a bit, by more than 100 kilojoules per mole. And so that reaction there does not work. So in the next video, we'll talk about some of the subsequent reactions that occur after you've done these initial reactions with OH, either addition or hydrogen atom abstraction.